Janek. Cześć. Cześć. Dawno cię nie widziałem. Nie słyszę.
Cześć mówię.
Cześć, mówisz cześć.
No miło cię zobaczyć.
Gdzie ty jesteś? Ty jesteś na Korfu czy to?
Tak.
Aha.
Dużo osób tu przyjechało nawet.
Ile jest osób? Znaczy, naprawdę.
Z 80 może?
Wow,
No,
naprawdę.
łącznie? Tak.
Fajnie.
Okej.
Okay.
So maybe we should start in the room. Okay, so I'm Stephen Ober. I will be your chairperson for the talk. So welcome. The first talk this afternoon is going to be Thomas Taylor, who's talking about celestial amplitudes, and I'll give you half an hour. Would you like a warning when you're getting towards the end, or can you?
Sure. Thank you.
So I'll give you a warning 5 minutes from the end.
Yeah. Okay. Very good. I never gave a talk in a hybrid format, so this is sort of like an unusual feeling because on the other hand, I see people on Zoom. I don't know see anybody in the room. So okay, but anyway. So thank you very much for inviting me to give this talk. Do you see actually there are two ways I can go like that, or I can go full screen. Which is better?
So, what were the options? Well, one thing is, could you turn your sound up a little bit because I can't hear you very well. We can't hear you very well.
Okay, all this.
I would say the previous one was fine. It was full screen, the previous one, but
yeah. Actually, this is a small. I use.
That's fine.
Yeah, that's fine.
I don't use landscape. I use
it's fine.
Which looks very weird. Okay, good. Okay. So anyway, as you probably know, there are two workshops running in Corfu. Actually, one ended yesterday. So there's this workshop. And the workshop on celestial amplitude and flat space holography was organized by Angelos Fotopoulos, Stefan Stieberger, Andrea Pum, and BC. And it just ended yesterday. And it was 5 very intense days of talks and discussions about the topic that I'm going to give you some little short. My original plan was, of course, to come to this workshop and then participate from remotely in the Corfu workshop on celestial amplitudes. But okay, these plans fell apart. So as you see, I am where I am. Okay, good. Anyway, so workshop isn't this, so I should start by a little tribute. So this is the School of Athens. It's a famous painting by Raphael, which you can see in the Vatican Museum in Vatican City. And so you see here Plato and Aristotle as two central figures. Well, actually, a central figure is Diogenes the Cynic, a famous philosopher, so to say, who was a rather extravagant person, and so everybody kept staying away from him. So somehow, everybody is keeping safe distance from him. But anyway, what I want to focus is at one end of this painting, which you see here. I hope that I'm doing, okay, well, here. On this end of the painting, you see that part of the painting. First of you see Ptolemy with Ptolemus, I think that is in Greece, holding celestial sphere, who is the subject of my talk. And then here is a very interesting of this painting is Euclid, who is talking about Euclidean plane, which is of course related, as I will explain, to celestial sphere through stereographic projection. What is really amazing about this picture, look who's surrounding Euclid. There are students, I know, like 4 or 5 students, and all of them are women, which is quite amazing because the painting was done in 1510. Another very interesting thing about this painting is, if you look carefully, you will see that Euclid is wearing a mask. Well, okay, that's how it looks like. I didn't make it up. It's a wall painting, so it could be just a problem with the plaster, but that is what it is. Okay, so anyway, the subject of my talk is celestial sphere and amplitude, celestial amplitude. So in general, so it's this area, it's called celestial holography. And the idea of holography is that you want to describe 4-dimensional physics, 4-dimensional space-times, as a physics on the boundary. Some case it's a 2-dimensional sphere. And the idea is that in this way, well, first of all, it may be possible, yes, that that actually like 4 dimensions are a sort of illusion, while really whole action happens on a just lower dimensional sphere. So it's interesting thing whether it is possible to describe 4-dimensional physics. The whole holography problem is this description of space-time in terms of state of physics at the boundary. And hopefully also, as I will explain, maybe you can learn something more about 4 dimensions, if you 4-dimensional physics, if you think about it in these two-dimensional in terms of this 2-dimensional theory of 2-dimensional boundary. So the first question which you want to ask, what is the boundary of Minkowski flat or asymptotic flat like our universe space-time? Okay, what is the boundary? The answer to this is very simple. You just go outside on a clear night in Corfu. When you look outside and you see stars and skies, they are on what you see as celestial sphere all around us. And the way you can see it, the way to think about it, is what you see actually is all the stars and so on, which are very far away, long ago, which means that what you see here, essentially light rays, which you follow back to past infinity along light rays. So it is called a null infinity. So celestial sphere is essentially, you would say, null infinity boundary in that sense of Minkowski space. By the way, if you have any questions, please ask. You can ask them anytime. Raise your hand or whatever, or I don't know what is the technique, and then I will try to answer them during my talk. All right. Okay. So this 2-dimensional. So sphere is 2-dimensional, and that will be actually the arena for this celestial holography from the celestial amplitudes that I will describe in a minute. So you think about this, you can think about the sphere. Sphere represents essentially all possible directions in our space, directions of light rays here. And so it corresponds, so these directions of light rays correspond to the points on the celestial sphere. Now, there is the most convenient way to describe a sphere is describes it in terms of 2-dimensional plane. And this is done like in cartography by a so-called stereographical projection, which means that you slice the sphere in the middle with a 2-dimensional plane. This would become actually a complex plane, a plane of complex numbers. And for a given point, let's say given here, you associate a point on this complex plane, which you get by the point at which the line connecting this point with the North Pole intersects the plane. Okay, so that's the idea. And so for there is one-to-one correspondence between points on a celestial sphere, on the point on the sphere in general, the sphere is sometimes called the Riemann sphere, and points on the complex plane. And you see that the equator is mapped to a circle of radius 1. Everything outside the circle is northern hemisphere. Everything on southern hemisphere is mapped to the inside of the circle. Okay, and this is just regular stereographic projection, which we use actually to do what we call complexifying a sphere, projecting a sphere onto a complex plane. Now, okay, so that's very simple. That's like elementary geometry. Now, there's something which is very interesting, which is not so obvious, but it was, I think, first discussed by Penrose in 1960s, is the following thing that happens. Okay, so suppose that you are here and you see celestial sphere, all these stars, galaxies, whatever, in all possible directions, yes? You may ask the question, how this night sky looks from a very fast-moving spaceship like Millennium Falcon in Star Wars or wherever it is, okay, which is moving very fast. Let's suppose that the spaceship is moving, okay, at the speed comparable to speed light, in the north direction. What you find is that, contrary to some intuition, that the stars and galaxies pile up in front of you. So from inside the spaceship, you would have the celestial sphere would look like that. Stars and galaxies would pile up towards the North Pole. They are dragged away from the South Pole. So in other words, from the point of view of complex plane, the points are shifted more north-polish towards infinity. And actually this Lorentz transformation, in this case, Lorentz transformation of celestial sphere, corresponding to simply rescaling on the complex plane by actual exponential factor, which depends on the rapidity. So the faster you move, the more dramatic this effect away. And essentially, it's a uniform rescaling in all directions on two-dimensional sphere. So the Lorentz boost, okay, in this case, in north direction, is a two-dimension dilation, a scale transformation. So that is a very important point, that the Lorentz transformation, this one boost actually is realized as scaling as in two dimensions dilation. In general, actually, all possible, you have three boosts and three rotations, and that actually altogether, when you look how what happens on the complex plane when you perform Lorentz transformations and see celestial sphere from different observers, the transformations become actually so-called, okay, I start from scaling, so you know from four-dimensional physics, scalings are like conformal transformations, and these conformal transformations are realized in this way on these complex coordinates. Okay, so that's one thing which is well known, that actually Lorentz group becomes a group of conformal transformation on two-dimensional celestial sphere. Now, this sphere, on the other hand, okay, I was telling you these are directions, correspond directions of light rays, the light rays which are coming out from far past. And so actually we can think about you can think about the scattering processes in the following terms. You can think that you have this, when you want to talk about scale, when you want to scattering processes, let's assume of massless particles, which are moving at the speed of light, okay? So we have these particles which are moving from celestial sphere, okay, from the past. They interact and they fly away to infinity. So the scattering processes, you can think about transitions between various, particles localized at different points on celestial sphere. Okay, so that's the starting point for all this construction. And actually, if you look at four-dimensional momentum on shell, let's say it goes like momentum, you need actually three parameters to parameterize it. One is, of course, the direction, for which you can choose this point on a celestial sphere. And then you have, in addition, of course, you need energy. Yes, so we have three parameters: one direction, which is this one complex parameter, Z on celestial sphere, and one energy. And this energy, in order really to discuss the scattering, you have to think how to represent energy. Yes, okay, in terms of something on celestial sphere. So, in other words, you need to. So, once again, we think about scattering processes in which you have. Incoming particles coming from different points of the celestial sphere, scattering and then running away and flying to these final destination on celestial sphere. So we need to encode not only information, not only about directions of these particles, but also about energies, and we want to do it in a Lorentz invariant way. And there is a way of doing that. The way of doing it is to, the way to do it is as follows. Normally, when you talk about scattering processes, you think about scattering processes like you see the particles with certain momentum coming in, and the particles, and then you measure energies and momentum of the incoming and outgoing particles. Yes, and that for that you know how to compute the scattering amplitude. Now, in order to translate it into language of scattering processes on celestial sphere, we simply can change basis from the momentum basis, a plane wave, to the basis of so-called conformal wave packets, in which essentially trade the energy into a quantity which is just dimension of the wave function. So conformal wave packets have different dimensions. They're labeled by dimensions and by this direction of the momentum, which is left over from the plane wave. Okay. Formally, what you do, you will simply replace start from the plane wave and perform something which is called Mellin transformation on the plane wave, and this trades the energy omega into dual variable, which is dimension. And this conformal wave packet has, for example, when you boost it in direction of the North Pole, okay, will be actually rescaled will just be rescaled. Okay, so it would have a good, it will be eigenvalue of boost. Sometimes when you talk about these conformal wave packets, we talk about the boost eigenstates as contrasted to plane waves, which are a translation, which are momentum eigenstates. Okay, and so you can do it actually. So you can trade energies into these dimensions, and then there's one thing which happens that when you get asked, you want to talk about normalizable wave packets, so you talk about them, you find that they can be normalized only if dimensions have very special form. They are of the form 1 plus I times real number lambda. So this type of wave packets, I usually call them, they belong to something which is called principal conformal series. So now what we want to do, we want to translate usual scattering amplitude, which is like between in and out states with a given momentum and momentum and energies. And again, I'm talking about scattering amplitudes of gauge bosons, gravitons, as in massless particles described by Young's theory and Einstein's general relativity. So normally what we do in momentum basis, you compute, you do Feynman diagrams, compute this invariant, Feynman's invariant matrix element. And then in addition, you have a momentum conserving delta function. And so this is what we normally do. Now what we are supposed to do, we are supposed to take a Mellin transform, but we start again from this amplitude, which is written here, okay? And you perform Mellin transformation and trade the energies into these dimensions, which essentially now are parameterized by one number, this lambda parameter. Okay, which plays the role of the dimension. In this way, you translate four-dimensional amplitudes into matrix elements, which are characterized by the positions on celestial sphere and dimensions. So in this way, you translate the scattering amplitudes into correlation functions of conformal wave packets. And these wave packets are also called sometimes primary fields, okay? So this allows, so this is what I explained right now, is actually a definition of celestial amplitudes. The celestial amplitudes are the scattering, regular scattering amplitudes, which are written as conformal basis of boost eigenstates. Okay, so you're using different bases. Okay, that's one thing. That's a starting point. Okay, so now what is very interesting, and what this whole sort of research field started, is that because this construction is rather obvious, okay, is that 8 years ago, Andy Strominger showed that such correlators, actually in hiding the four-dimensional scattering amplitudes, have a symmetry which is much larger than the original Lorentz symmetry that I started from. What he showed that essentially there is infinite dimensional group of symmetries, which is you can not only boost, which consists not only in a boost annotation 6-parameter group, but a whole infinite dimensional group, which corresponds to all possible smooth deformation of the sphere. And so on complex plane, this corresponds to conformal, you would say, local transformation, in which the general coordinate transformation on complex plane, in which any point z is mapped to point with coordinates which are an arbitrary holomorphic function of z. And so in other words, this four-dimensional S matrix, when written in the celestial basis, shows infinite dimensional symmetry, which is a symmetry of the diffeomorphism of a celestial sphere. So, and these two-dimensional conformal transformations are generated by infinite dimensional algebra. This algebra, you may remember string theory, is called the Virasoro algebra. Okay. So the goal is, and actually, I should also mention that the symmetry can be also viewed in a little bit different way. You can these transformations are called super rotation, and already for I don't know 50 years it is known that actually asymptotic flat spacetimes like Minkowski have infinite dimensional symmetry group of the solutions of Einstein equations, which is so-called BMS or Bond-Metzner-Sachs symmetry. So that symmetry of general relativity is realized somehow in some fancy way in four-dimensional scattering amplitudes. So the goal is to construct, since we are talking now about correlators on a sphere, correlation on a complex plane with definite dimensions. So this is, and the underlying group is conformal group. So we want to construct celestial conformal field theory in 2 dimensions that would describe 4-dimensional elementary particle physics, okay? Which is, with the first thing, we would describe scattering amplitudes. And hopefully, once we understand it better, we will have another track beyond the standard model, the one that I am personally interested in always, and is some type of a possible gauge gravity unification, which was previously attempted within the framework of string theory. But now I think this looks like actually a very interesting and promising avenue to try this from a completely different perspective. So let me just explain. You say, okay, so far I was just talking, and I didn't give you like a concrete example how it works. It's actually it sounds very vague, but so let me give you a very concrete example, concrete example how it works. This 4-dimensional, 2-dimensional dictionary works within this framework of celestial holography. What is very important, what plays very important role in this discussion are so-called soft theorems, which you use all the time at the late C and everywhere. Well, like for example, here, that when you have let's think about scalar QED, you have some charged scalars, then of course they emit photons, and you know that when it's soft photons, you have soft photons in 4 dimensions, you have infrared divergences, and there is a well-known formula for that. It's I think Willows or Weinberg's formula, which describes that. and with this scattering matrix with one soft photon, it can be written in terms of the amplitude without the photon multiplied by the soft factor, which diverges when the energy goes to zero. Okay, so this is the soft theorem. This is the leading soft theorem, something which which we have in the in one of the first lectures when course on QED. So this is something which is very well understood. Now, how does it look at the framework of celestial holography? Well, here you have the scalars, and now they are labeled, of course, not by momenta, but this positional celestial sphere and dimensions. And actually, this limit of soft photon corresponds to the limit when the corresponding operator on celestial sphere, lambda goes to zero, which dimension goes to 1. And then what you can show that actually when you write the celestial amplitude and the limit when dimension of the photon operator goes to 1, you get singularity, which reflects actually the original infinite singularity of 1 over omega, multiplied by the again, it factorizes into the amplitude without the photon, but now it's a sum essentially of in which you take you multiply by this, multiply each which have sum of all each charge and divided by the z minus zi. Now, if you okay, I have no time to go into detail, but this is nothing else than something which is called Ward identity of two-dimensional current. Okay, so in other words, the soft photon, conformally soft photon, dimension 1, corresponds to a Goldstone boson of some asymptotic gauge symmetry. So you translate soft theorem into a statement about the symmetries and the symmetries and word identities of symmetries of two-dimensional conformal fluid theory. Okay, so that's that's one of those things. There are many other, and this whole soft. That's why this research on celestial. So this whole research and celestial.
So you have 5 minutes left.
Yeah. I will do it. I will finish a couple of minutes. So this whole research about research on celestial holography led to actually like a renewed interest in discussing the soft limits of scattering amplitudes, and so that's that is a completely okay. The research area opened recently, and then there's this whole thing which you see about these two-dimensional currents. So this is related to conformal field theory, and this relation is really very, very interesting and leads to some interesting conclusions. It's also related at the end to some there are similar theorems which describes not just photon scattering of charged scalars, but of course there are similar theorems which describe soft gravitons, and these theorems are apparently related to something which gravitational memory effects. There are lots of interesting things that you can do with it. So in conclusion, we have this celestial holograph is a proposal for a holographic description of flat space-time in terms of the celestial conformal field theory, and hopefully that will lead to better understanding of four-dimensional physics. There are many things to be done. So I already mentioned that Corfu workshop ended yesterday. There's a next one coming out in Edinburgh in a couple of weeks. And actually, during this Corfu workshop on celestial holography, there were many people who were saying, "I wish I could go now and on the beach have a nice dinner." And they're looking. I think people were really disappointed that, to tell you the truth, that the conference was remote. Well, that's the times, yes, so we have no choice about that. But I'm sure that everybody would be happy to come back and see Corfu and enjoy a workshop which would happen in person, hopefully in the future. But there are many other conferences coming up, and so there's very active research area, because essentially it combines really some type of it combines the most active research areas, because on the other hand, you have amplitudes, yes, which are already the active research area. There's this conformal field theory, which is again which is in 2 dimensions, but also in higher number of dimensions that will discuss some conformal invariant generalizations of the standard model and so on and so on. So it's a very interesting topic and combines also general relativity. So it's really a topic in which you can combine the various techniques, and so it's a fascinating research area. And I hope that I was able to give you at least some feeling what it's all about. All right, good. Thank you very much.
Okay, so thank you very much for that very clear description of what the excitement is all about. So do we have any questions from the room? Apostolos Palafsis.
Okay, so I'm not so expert exactly what you are going to. I'm not so expert exactly what you are going to do. But as far as I know, you have a part space. Usually, in general, like you are going to do, it's difficult to define as a topic space because it's a orthogonal system. Like if you have it on a sphere, for example, there are no orthogonal states. So in order to define a scattering amplitude, you need this orthogonal Hilbert space. I don't know from where you can get it in this description. I know only for operators, but I don't know how you can do it.
For way, the simplest question is about wave function. Yes, so these conformal wave packets are orthogonal, but with a norm which is so-called Klein-Gordon form. So there's a concept of orthogonality and complete basis, and so these conformal wave packets are a good basis. That's what it looks like. Yeah. So these are asymptotic states. It's different basis, and it's an orthogonal basis.
It's on a curved space-time. I mean, right?
Yeah, okay, okay. So yes, on space-time, yes.
Anyway, it's quite surprising, but okay.
Okay, so any more questions in the room?
Yeah.
No? Is there anything online? No, okay. Okay, so there are a number of questions. Thank you very much for the talk. It was very good. Thanks again.
Okay, welcome. Great.
Yeah.
I have the point.
Right, okay. So the next speaker is Sarkis Dedis, who's going to talk about standard model effective field theory.
Thank you very much. I would like to thank first the organizers for their kind invitation. Yes, as Steve said, I'm going to talk about scalar leptoquark matching onto SMEC, following a functional approach. Okay. So the outline of my talk, I will first introduce you to the functional matching techniques. Sorry. Then I'm going on with universal one loop. I'm going to discuss my recent work with my student on universal one loop matching for scalar leptoquarks, and I will demonstrate the results of this matching onto scalar leptoquark model S1 plus S2, and then I will end up with conclusions. Just some history on of matching to EFT. As we all know, EFT is a robust way in searching for BSM physics. It ranges from particle physics phenomena all the way up to nuclear and molecular, atomic and molecular physics. So what we discuss usually is heavy fields integrated out from a known UV theory, the so-called Apelquist-Carozona theorem, and then what this theorem says is that at low energies we have a tower of operators, high-dimensional operators that are produced, and also renormalizable couplings that are affected. We usually put these operators into certain bases. Bogdan has one, and collaborators, and or even just leave the operators without taking equations of motion into account. Until recently, the matching technique was mainly Feynman diagrammatic, although last decade an old functional matching technique initiated by Gaillard has seen a renewed interest. The first universal results are encoded in what is so-called one-loop universal effective action. This is an action that contains heavy fields that are decoupled, and it is one piece of action is not really is not the full story, but because it does not account for mixed statistics and open covariant derivatives or heavy light. At the beginning, it didn't account for heavy light particles in the loops, but then recent advances in ULIA in this universal one loop effective action encoded the statistics, mixed statistics scenarios, so different different particles in the loop, but still the whole picture is not far from over. Meanwhile, covariant diagrams, a technique, a functional technique that mimics the Feynman diagrammatic technique came along, and these covariant diagrams are at all steps gauge covariant diagrams, and make use of the expansion by regions and a simpler matching framework. And finally, last December, a paper by Cohen, Liu, and Zhang came along and they introduced a new technique, well, based on covariant diagram techniques, a technique called Superplace functional technique, which establishes a cleaner way to display covariant diagrams for matching. And this actually technique has been automatized through two codes. One is the stream, and the other is the Superplace. So it is exactly this particular one approach that I'm going to follow in our that we followed in our work. Advances on this topic include a paper by Apostolos that I'm sure he's going to say a lot in his talk. So let me give you a brief idea of what is the Superplace functional matching procedure is. So the basic formula. So we deal with one PI, one particular reducible actions. So we have the UV action on the right-hand side, okay, here, with the light fields. Phi here is a collection of light fields, which has to be equal with the EFT Lagrangian EFT 1 PI effective action with the light field. So we equate both, and we just define the Wilson coefficient. So at tree level, so this is we do not equate amplitudes. We equate off cell. We equate one PI. Okay, one loop, one particular reducible effective actions. So at tree level, what we do is the following. We have a heavy field. I will call it S. Say that this field is the leptoquark. This is a collection of leptoquarks. So what we do, we take the equations of motion for this field, and then we plug the result back to the Lagrangian, and then we find the effective action. At one loop, the story is a bit more complicated. Following this superplace functional technique, the one loop effective action, the EFT action, is basically the sum of two terms. The first term is a sort of universal term, is a supertrace log of a K. K is a matrix that contains the propagators. Supertrace comes, the definition of supertrace is that for fermionic blocks in this K matrix, I just put a minus sign, nothing more than that. And I have to calculate this in a hard region, namely in a region where the momenta is of the order of the heavy fields. So this part of the action is really known. It can be tabulated, and there's nothing more to say about it. It is a part of the ULE, of the universal one-loop effective action. What is really not known is this part here. So this is a series of supertraces with the inverse, with propagators, k to the minus 1, times x. X are field-dependent vertices. These are operators that act on the field space, and this look like these terms can be graphed as normal with Feynman diagrams of this size. For example, x denotes a vertex, and k to the minus 1 is a propagator. So if you take, for example, n equals 3, you have 3 vertices, 1, 2, 3, and 3 propagators. One of the propagators has to be the heavy field that is being integrated out. So, for example, here is the leptoquark field, Si, and the other F and F prime are the two fermions, two standard model fermions. Can be quarks, leptons, etc. So what we do, we just sit down and write diagrams with at least one heavy particle, and we just find the diagrams, the supertraces of these diagrams. So I'm going to discuss this technique in specifically for scalar leptoquarks. So this is what we did, as I said, with my first year student, a PhD student, Kostas Matsaropoulos, where we derived the universal one-loop effective action after decoupling all scalar leptoquarks in green basis, in a basis before equations of motion taken into account. And we did the matching up to dimension 6 operators at one loop, and demonstrated the usefulness of the results in calculating several observables such as leptonic, magnetic, and electric dipole moments, neutrino masses, proton decay rates, the Higgs mass, etc., in a model with two heavy leptoquark fields. Some of these results I'm going to display today. So in this particular scenario, we produce almost all the operators, almost all operators in Warsaw basis, 54 out of 60, all but the bosonic CP-validating ones. And to my knowledge, this is the first study of functional matching that compares with the Feynman diagrammatic matching and finds exactly the same results for some of the cases, okay, where they exist. And it supports the usefulness of the supertrace functional matching. It's because over other methods, either functional or Feynman diagrammatic, because of its simplicity. Okay, the steps for functional matching are the following. First, find the tree-level EFT. Okay, as I mentioned it before, for leptoquarks, only 4 Fermi interactions appear at 3 level, and this is quite useful for phenomenology. Second, we find these X matrices. This is very easy for the first term, for the U matrices here, because just take, the only thing that you have to do is just take the second field derivative of the UV Lagrangian. But then you have open covariant derivatives that come alone, and this is a P mu here denotes a covariant derivative times Z, a matrix that has to be found by the Lagrangian in the Lagrangian. Okay, and these dots here denote higher order operators. So if one wants to go beyond that dimension 6 operators, one has to include more terms in this expansion. So we found all these X matrices for all 5 scalar leptoquarks. Then we enumerate the Euler terms and the superplace diagrams. There are 19 terms in Euler, and then there are 15 superplace diagrams to evaluate. One superplace diagram is this that produces the neutrino dimension 5. Among other things, it produces the dimension 5 Weinberg operator. So then we have to calculate the one-loop diagrams, these supertrace diagrams using dimensional regularization in MS bar renormalization scheme and in Feynman gate. So a typical calculation of this diagram, calculation of this diagram reduces results in such a term here. This is a finite diagram here. The only thing that one has to do is to take a normal trace of various matrices. And then at the end, we add up the 2 Lagrangians, the 3 Lagrangian, and the one-loop Lagrangian. Let's see how this works in a particular scenario. Okay, let's consider 2 out of 5. We have 5 scalar leptoquarks. Let's consider 2 heavy leptoquarks. Okay, one is the S1, which is a color singlet, and the other is the S2 tilde, which is a color doublet. Okay, so I have the standard model plus these 2 scalar leptoquarks. Then we have new interactions with quarks and leptons. For example, this S1 color singlet will couple to the quark and lepton doublets, or to quark and lepton singlets. This S1, unfortunately, it will bring over proton. It will bring barren number violating couplings. For example, S1 will couple to 2 quark doublets or 2 quark singlets. And the S2, the color doublet, will couple to either to quark singlets and to lepton doublets. Okay. This S1, these 2 scalars will bring also new interactions with the Higgs, and these are the most general interactions that one can write down. We have H square, S square terms. We have a trilinear term between the 2 Higgses, the two leptoquarks, S1, S2, and the Higgs. This is a dimension full coupling. And we have another baryon number violating term, which consists of only S2 fields and Higgs. And then finally, we have self-interactions among leptoquarks. Okay, we go 3 level. We do we follow the procedure that I described before, and then we have 12 baryon number conserving operators. These are mostly semi-leptonic and 4 quark operators. And then we get all baryon number, the complete list of dimension 6 baryon number violating operators, and these are all this. Okay. So here we have a model where it violates even a 3 level baryon number, so one has to do something about it. So what usually is quoted in the literature is that we have an extra symmetry on top, and probably ad hoc symmetry on top of this, and we kill this Yukawa terms. Or another solution is to take M1, the masses of the heavy fields to be up to the 10 to the 13 GeV or so. So there are two phases of this model, in my opinion. One is with low energy, but with symmetry and force with the symmetry, or at very heavy scales, with where the symmetry is, where proton stability is sort of natural. So, because this model produces only 4 fermion operators, it is suitable for explaining possible anomalies in meson decays, and this has been done in many papers in the literature, and also there were many talks even in this workshop. Well, let's see some aspects of this one loop effective action. So we have written down the full effective action. So let's see what we can learn from this. Let's go to the renormalizable operators first, and just check the first thing, which is the corrections to the Higgs mass. Okay. So this is delta m square over 16 pi square. So this is delta m square here. L1 and L2 are just these logarithms here. Mu is the renormalization scale. Okay. And delta 1, 2 is just this square mass difference. We see that if these guys are heavy, the leptoquarks are heavy, very heavy, then we have a destabilization of the Higgs mass. As we all know, the scalars will try to push the Higgs mass up to their scale. But also we see a contribution from the other dimension-full coupling that we put in the Lagrangian. So the Higgs mass displays a sensitivity to all dimension-full Higgs parameters. So you understand? Okay, we started with effective field theory, where the Higgs mass is a part of the light fields. So here, if this M1 is really huge, and the couplings are of order 1, then the Higgs mass will just leave, and it's not a light field; it becomes a heavy field. So this is, of course, it's not allowed in EFT, and so I call this perturbation theory instability. So one has to do something about this. Okay, possible solutions are all we all know. Either these leptoquark masses are light of the order of TeV, and couplings, these lambda couplings, are of order 1. Second, leptoquark masses are at high scale and couplings are very fine-tuned. Or third, one can choose a particular renormalization scale nu, such that these logarithms are -1, and then you can trivially check that delta m square equals 0, and from then on, the Higgs mass is only multiplicatively renormalized down to the top quark scale. So the perturbation theory is under control. Or just take the supersymmetrization of the model. That is, you introduce another spinorial superpartner that cancels this hierarchy, let's call it. What is not normally quoted in the literature is the sort of fine-tuning in non-normalizable operators. For example, let's take one particular operator, this one, semi-leptonic operator, and calculate the one-loop corrections, as we did in the paper. So you see that these corrections come with ratios of the masses of the two leptoquarks, m1 square over m2 square. So if there is a hierarchy between the two scales, then this, again, we come to the same problem. I mean, we have this perturbativity type of problem. This becomes this term here becomes huge, and this spoils the perturbativity. So it's sort of it seems that the two scales, the masses, seem to favor. I mean, it's better. You better take the masses to be of the same order of magnitude. but it's quite a similar problem. Or tune the couplings or take L1 equals to -1. Of course, this L1 equals to -1, I cannot justify it by a symmetry. I just, it's not something that comes with the symmetry. And I don't even know if it stays at the two-loop level or so. Okay, another aspect of this model is that you get immediately from the super diagram that I said before, that I drew before, you get the Weinberg operator, the dimension 5 operator, so you get neutrino masses immediately. These masses are finite in this setup, and they are sandwiched between they're proportional to the lepton number violating coupling of the Higgs sector that I said before, and sandwiched between the leptoquark Yukawa couplings and the down Yukawa coupling. Another aspect is to work out the G-2, and this is very easy. Once you have the 1pi effective action, everything is easy. I mean, in terms of observables, it's not a long way. So, as we all know, the G-2, the lepton G-2, is affected by mainly by two operators at 3 level in SMEF, and these are the EW and EB dipole operators, which are given here. So, since we did the one-loop corrections, we find the corresponding Wilson coefficients in Warsaw basis, and then just because these are observables at one loop, the only thing that we have to do in order to compare with fixed order calculations is to leading log, is to just set mu equals m top, or we just start running from the heavy scale down to the m top by using the RGs, plug it into the Lagrangian in the mass basis, in SMEF mass, and then the Lagrangian that gives you, once you have this Wilson coefficients, you get the non-anomalous magnetic moment, and then you get the result that we all know from fixed order calculations. So in this result, it's obvious that we have an enhancement, because when Q is the top quark, we have MT here. So it's naturally, G-2 for the muon is naturally, let's say, enhanced by the of order. I mean, we have a chiral enhancement of order of m top over m mu, and one can solve the anomaly for TV S1 mass and order 1 coupling. I have to say that the same supertrace diagram gives also corrections to the muon mass. It's exactly the same term. And once we try to solve, let's say, the G-2 problem, you have big corrections that are going to the muon mass. So you have the running mass plus the one loop corrections, and you always need a sort of fine tuning to get the muon mass at the given value. Yeah. Conclusions. So I described functional techniques to matching. So it is indeed they give several universal results, and in our work we used supertrace functional and universal one-loop effective action matching, which is I believe the simplest framework we can work out. In our study, we found all seeds for universal matching of scalar leptoquarks, basically all X matrices on all the diagrams, all the corresponding diagrams. The only thing one has to do is to plug in to take the traces of these matrices, and I discussed really an example. There are some technical aspects that I didn't have time to go through. Technical discussion on evanescent operators and RG checks. I discussed an application of two scalar field model. So we did, as I said, we did all
Okay, thank you very much. Yep, Apostolos.
Very good, very nice. The only thing is confusing me is your construction, even though you say light and heavy, you know, so you have to have a cutoff. So in order to integrate the heavy modes, right, so you use all the time dimensional regularization. You know, from dimensional regularization, you integrate both infrared and ultraviolet modes. How you can justify that and don't use, for example, a cutoff regularization integrating from the threshold modes to infinity? I understand these are UV finite operators we integrate, but why you are using dimensional regularization instead of cutoff?
sorry. You can use this integration by this. You can use this expansion by regions, where you just separate the integrals between soft and hard regions. So you immediately find that the soft parts of the UV and the EFT cancel out, and what remains is the hard one within the dimensional regularization scheme. So it's kind of and you match with the cutoff. No. No. You take the hard part of this of the UV and the EFT, and this is what enters in the game in the end. It's not the soft part. This cancels out, which is sort of magic. Yeah.
Hello. Thanks for a nice talk. I'd like to ask your opinion about the automatization of this process. I think there has been some recent attempts in the bibliography. Like, how far are we from, you know, defining particle content and getting the matching automatically for any theory? What are the main
I think we're not far. So for the most difficult part, which is calculating supertrace functional integrals, has been done. And there are two groups that have done this. They seem to agree. We used both codes, and it seems everything is working fine. So the difficult part has been done. I think there are some technical aspects of anomalies, how to treat gamma-5 matrices when you have traces, when you have fermions in loops, how you can extend this to arc-side gauges, several technical aspects that I think they will be solved in the near future. And then what it matters is just coding the final result.
That would be spectacular.
I think we're probably better move along anyway. Thank you very much again. So the next speaker is Sigmund. Yeah, well, I mean, thank you. Good evening, everyone. It's a great pleasure to be here again, especially after this forced break. Great thanks to the organizers for giving me this opportunity. Maybe I should. No, okay. Here's the talk, and its title. Actually, I'm going to summarize in a number of slides. So work on unstable domain walls, which has been carried out in Warsaw over recent years, mostly with the effort of younger colleagues Marek Lewicki, Paweł Olszewski, Tomek Krajewski, Janek Kwapisz, Olga Czerwińska, Łukasz Nakonieczny. Those are the names which I'm obliged to mention. So the most recent work has been put on archive earlier this year, and that will be the final part of my presentation. So before I go to the actual topic of domain walls, let me give you some background. I mean, the model background or particle physics background which motivated us for these studies. So first, I shall talk for a while about standard model and beyond the standard model effective potentials with non-equivalent vacua. Then I shall discuss the issue of the domain walls as possible late traces of the early universe physics stemming from the existence of those non-equivalent vacua. Then I shall discuss the issue of the finite temperature corrections, and finally I shall talk about the possibility of observing gravitational wave signals generated by decaying domain wall networks. So first of all, the broad picture, models of interest. Well, it all started with the issue of radiatively generated minima in the standard model, for instance, in the standard model large field strength. But even earlier and after that, the issue of runaway potentials, I mean, those potentials which are characteristic for the effective potential, stringy effective potential for the moduli, like the stringy dilaton or stringy T modulus. This is essentially the overall shape which appears in the context of the non-perturbative potentials generated for the stringy moduli. Somewhat unexpectedly, similar structure appears in no-scale extensions of the standard model. I shall present such a model somewhat later. Again, the standard framework for discussing the topological defects and including domain walls are models of strong first-order phase transitions, where the bubbles, usually the dense gas of colliding bubbles
and where thermal effects play a significant role. It will turn out that actually in the context I am interested in, the thermal effects will be subdominant. Then there are other models with non-equivalent vacua, like axial monodrome models and relaxion models. I shall not discuss the physics of those models in great detail. However, the techniques and the general framework I shall discuss at the end of the talk applies also to this type of potentials. Well, in all those potentials, we have non-equivalent vacua with different vacuum energies between transitions, between which transitions are possible, and those could be transitions due to tunneling, quantum tunneling, or transitions due to certain quasi-classical effect like thermal fluctuations or other type of mechanism creating various, non-trivial initial conditions for the evolution of the universe. Now, here's a brief recount of the story leading to the second large field strength minimum in the standard model. Well, this is essentially due to the running of the quartic coupling in the standard model, which at certain scale turns the effective potentials, the loop effective potential, towards the negative values. This used to be a hot issue several years ago, and the issue discussed over by now, well, maybe with lower intensity right now, but still pretty interesting. Now, the point is that since this is a loop effect, radiative corrections are involved, then there is a place for the role of new physics, for possible role of new physics, which goes beyond the standard model. So I guess that's why this issue got so much interest at certain point. Namely, any correction could change the picture, could change the lifetime of the electroweak vacuum. And the study of this issue has been performed extensively by many groups, including the Warsaw group, and most of the study was based on adding certain effective operators involving the Higgs field to the standard model. It turns out that actually adding certain corrections, well, maybe I skipped the slide which actually presented the form of the corrections, but those corrections are simple monomials in the scalar field, say in the scalar component, in the neutral component of the Higgs field. So they are of the form lambda 6 times phi to the 6 over certain scale of new physics squared, or higher order terms like lambda 8 times phi to the 8 over the scale of new physics to the power 4. So those were simple operators disturbing the effective potential of the Higgs field, and the influence has been extensively studied. So the point is that with such a innocent addition, you can change the behavior of the standard model. You can change the fate of the universe. Namely, you can create additional minima if you adjust suitably the scale of the new operator and the sign of its coupling, or you can destabilize further the standard model, but at a lower scale. I mean, producing a new minimum, additional new minimum at the lower scale than the one which naturally appears when the quantum corrections are being calculated in the pure standard model, or you can also stabilize it completely by choosing the right scale of new physics. Here it is 10 to the 8. Yeah, this picture corresponds. This is the effective potential when you add the operator of the form 1 over 10 to the 8 to the power 2 times Higgs to the power 6. So the new minimum disappears completely. If the suppression scale, the scale of new physics gets higher and higher, then of course the standard picture reappears slowly. So that's a general picture, and those are the possibilities. So the corrections to the standard model, to the effective potential of the standard model are worth studying, because they might influence, they actually easily influence the metastability of the electroweak vacuum. Now, here another modification of the standard model, the so-called quantum scale symmetric effective Lagrangian. I'm mentioning it not because I believe it's the ultimate extension of the standard model, but because in this model, at the level of loop corrections, an instability appears as well, and this instability is interesting because it's actually the instability which is very much like the one, actually much stronger than like the one which appeared in the business of the stringed dilaton, namely the second vacuum of the standard model becomes infinitely deep in this model because of the scaling solutions, of the scaling properties of the effective potential. Simply here, in addition to the Higgs field, you have a dilaton which mixes with the Higgs field, and if you go far away in the radial direction, along the say angle at which the zero of the quartic coupling appears, then you can create as negative vacuum energy as you wish. So there is a real instability in that model. However, it turns out that the details of what happens behind the barrier, beyond the barrier, are not so important. For the models which are based on the standard model, so which do not depart from the standard model too far, the tunneling, even though it is there, is not sufficient to create too many bubbles. It's not sufficient to create too many bubbles of the beyond the barrier vacuum. So it's not sufficient to, well, it's not sufficient, so to say, to create real. I mean, by means of statistical reasoning, a real danger to the standard model. Now the question is whether, well, all this reasoning has been performed in the context of the flat space, in the flat background. The question is whether, including actual gravity background, so the sitter or radiation dominated or matter dominated universe changes anything. Well, this issue has been studied as well, and it turns out the corrections are not substantial, so they don't change qualitatively the overall picture. So I will skip this part. Now, the question is whether there could be any trace left of all this story in the present universe. We know that eventually, well, that our part of the universe has landed in the correct electroweak vacuum. So what we see around is the physics which is based on the properties of that electroweak vacuum. So the question is, can one imagine any observable which would bring in information about the early universe, about the existence of that additional structure at high Higgs field strengths? So there are not that many options. One of them is actually the issue of topological defects, because if we have in the early universe, if we have several vacua, like two vacua in the standard model and the extensions I was talking about, then, of course, depending on the mechanism which creates initial conditions for the cosmological evolution, you might expect that in various independent causally disconnected regions, different vacua will be connected with certain probabilities. Then, if those vacua, if we have in the large part of the universe encompassing our horizon, such a selection of different vacua, then there is something to watch, because the behavior of the regions between separating those different vacua, might might be an interesting place. In first approximation, I shall talk about the regions separating different vacua in such a setup as of domain walls, although they are, from the point of view of the actual solutions of various equations of motion, they are at best approximate solutions of those equations. However, from the practical point of view, from the point of view of describing the structure of the large vacuum, of the global vacuum, this is not about description. So that's a typical picture. That's a typical picture of the global vacuum when independent choices of the vacua are made in the available portion of the universe. The first situation here is the one where the probability of choosing one or the other vacuum is equal. And that leads, as you can see, to a production of the sheet of a domain wall stretching through the whole universe. That's sort of an equilibrium situation, which results in the, in this, say, surface density distribution, which stays around for a while and scales with the expansion of the universe. And the other more likely situation is that instead of this big wall stretching across the whole universe, across the whole global universe, you actually produce the different vacua of different probabilities, and then the less probable vacuum forms bubbles, described by, limited by spherical walls in the sea of the preferred vacuum. And then this network, the energy is stored, of course, in the walls, which are limiting the region occupied by the false vacuum. But typically these walls oscillate and disappear. Of course, they also interact with each other. And when they disappear, they dissipate energy. And one of the channels, the energy dissipated is the emission of might be the emission of the gravitational waves. Of course, other things to which the field couples could be emitted as well, including its own radiation, including other particles which are coupled to it. But for the purpose of this talk, I shall ignore the other channels. I shall concentrate on the gravity waves. Now, here I have a few slides describing the evolution. This is the basic thing. The basics are simple, of course, the way you realize it in the actual simulation. This is a complicated story and demanding calculation, actually. This is this modified equation with certain coefficients alpha and beta in the Robertson-Walker universe. This alpha and beta should be equal to 1. In practice, one performs the so-called Press-Rydens-Pergel trick. Putting alpha equal 3, beta equals 0. This enhances the dynamical range of simulations, and after various tests, people believe this doesn't really change the qualitative behavior of the walls. However, I am mentioning this point because this is a subtle issue and concerning the propagation of gravity waves for the universe. However, we have to use this trick to watch the evolution of domain walls. Now, the other issue, which is crucial actually, is the initial distribution of the vacua in the universe. So typically, one assumes a Gaussian distribution around certain central value, which is somehow oriented towards the peak of the potential, towards the maximum of the potential, separating the two vacua. So there are two parameters which characterize such a distribution. As we know, there is a variance and there is a width of the distribution and the central value. In most simulations, I shall talk. Most pictures I will be showing the central value is simply taken to be located at the electroid vacuum, which on the scales which we use corresponds essentially to the origin of the scale of the axis. Now, what happens? Many things can happen. The point is that if you start with probabilities, with the initial distribution, which prefers slightly one of the vacua, the exotic one or the electroweak one, you can obtain various results. You can obtain electroweak vacuum as a result of the evolution after the bags of walls disappear, or you can easily obtain the exotic vacuum as the final vacuum. And actually, it is not so obvious, taking into account the separation of the two vacua, to expect that there are initial conditions which allow the electroweak vacuum to be the final result of the evolution. However, a numerical study convinces us that actually it is possible, and there is quite a wide range of parameters of initial probability distributions which are sort of natural, not so exotic, and so not fine-tuned, and still allow the electroweak vacuum to be dominant at the end of the evolution of the network. So that's the first conclusion. Electroweak vacuum could be a final state of the evolution of such a physical system, which is a good news. Now, of course, what happens is that the networks are of different nature. The networks created in various models with various initial conditions are of different nature, and they form networks which typically are not lasting for too long. So those are networks which rather quickly disappear. And the whole issue is to make to find the range of parameters in a given model so that the network stays around for a while, stays and scales with the evolution of the universe, so that it has a chance to emit a significant portion of energy in the form of the domain of the gravitational waves. This turns out to be possible. Now the question is whether temperature helps or not in this business. That's a question which has been asked many times, so let me briefly comment on that. The point, the basic observation here is that with the thermal corrections included, of course, those are thermal corrections due to the light fields, so the fields which are light at the electroweak vacuum, that the position of the maximum between the electroweak vacuum and the exotic vacuum, the position of that vacuum of that maximum changes. Namely, it moves toward higher field values. So that means that essentially wider initial distributions could be accommodated. So to some extent, it helps in the sense that the probability that in the hot system, the probability that you produce a network which evolves eventually towards the electroweak vacuum gets enhanced. So in that sense, thermal effects are useful. Well, now let's move towards the domain walls. The crucial observable here is the energy density in various modes of the gravity signal produced by decaying domain walls. Essentially, technically speaking, the origin of this gravity signal is the time dependence of the energy momentum tensor describing the network, describing these walls. And it's, well, the expression is sort of complicated. The really complicated part is to implement properly the numerical simulation for each configuration generated on the lattice from given initial conditions, and then to run it through various stages of the evolution of the universe. That's the real challenge, and this is a painful experience and very painful calculation, even numerical calculation, even taking into account the possibilities, the unlimited, so to say, range of the present-day computers. Now, one has to compute this energy density for various modes. K is the wave number. labeling various modes in the emitted radiation. Now you have to scale it to the present day. Well, I am using eta because it is conformal time which is used in all these simulations, and it's a technicality. And the other important parameter here is the peak density. So A is the peak frequency. So the signal, as you will see in a second, has a special shape. It's a shape of which has a form of a certain peak, and the frequency of that corresponding to the position of that peak is the very important characteristic of the signal. So that's the parameter which tells you whether the signal can be observed or not in present day experiments. So that's essentially the basic formula which have to be implemented in numerical simulation to obtain a result in sort of realistic extension of the standard model. This is kind of theoretical prediction. So those are these predicted signals. This is one of the early papers on the issue from 2015, and you can see that theoretical prediction at that time was pretty promising. So it looked like the signal from decaying domain walls, networks of domain walls, could cut into the regions penetrated by current experiments. That's why it seemed to be worth checking numerically in detail whether this scenario is realized or not. Well, as you see, the answer is negative, but it is sort of interesting how it is reached. So here's again the picture of how the topology of the typical domain wall network created the one which is used for the simulation. So at least the one which ends up in the electroweak vacuum. So here, these bugs, those are bugs of the exotic vacuum in the sea of the electroweak vacuum. So essentially, only such networks were allowed to be analyzed. So that's a typical configuration and typical evolution in terms of pictures. Now, thank you. Here is the result of the simulation. Those are the spectra which we have obtained via the numerical simulation, long and painful numerical simulations. You can see that actually the shape of those signals resembles the shape predicted by theory. So those are there are predicted peaks and wings of the signal, and that's the thing which you can see in the picture representing the actual numerical experiment. So somewhere here are the peaks. Here are the special features corresponding to the final stage of the decay of the domain wall network. So something like the ring out feature on that plot. So you can see that we get slightly higher energy signal. Here is the density, energy density. Here is the frequency. We get slightly higher energy signal for the model with somewhat wider distribution of the initial, wider initial distribution of the initial conditions. And this is not surprising because that means essentially if sigma is higher, that you penetrate the region of the field strength corresponding to higher values, higher energy scales. And that's why the overall energy scale available in the signal is higher as well. Now, how does it compare to the possibilities of the actual experiments? Well, the experiments are here, the signal is here, so the frequency is much too high to be anywhere near the sensitivity of the current experiments, and of course the strength of the signal seems to be too low. Now, What happens if you play with new physics represented by these operators I was mentioning before? Here are various examples of the network evolution. So this is essentially, those plots show you what is the portion of the lattice space occupied by the electroweak vacuum. So you can see that by small changes in initial conditions or in the scale or in the lambda 6, you can, in the value of the lambda 6, you can obtain very different solutions. So this one is preferred because you end up in the electroweak vacuum. These two are essentially disastrous. So those are options which you have, which you will examine, changing various parameters in that correction to the standard model potential. Well, here what you can obtain, maybe the next picture is more telling. Somehow this is the standard model case, which I was discussing before. Here are the best signals which we have obtained by playing with the, well, within reasonable limits, with this correction lambda 6 phi to the 6. So you can see that we were able to gain a bit, to go to somewhat towards lower frequencies. Here is the peak of the modified signal, and we were able to get up in the energy, but it's not a big. It's still, we are nowhere near the sensitivity of the current and future experiment. So the way we were able to raise the strength of the signal and to lower the frequency was to play with this additional piece of the potential in such a way that you make the difference between the energy of the two vacua smaller and smaller. You cannot make it too small because then you lose the you lose the power of your simulation for various technical reasons. So that looks like a large number, but that's the smallest possible difference between the vacua which we were able to follow during the simulation. Now, inspired by all this, we went on. Yes, so 2 slides left. Inspired by all this, we went on to construct generic potential, generic quartic potential. Actually, here it's even higher order monomial, higher order potential, higher order terms are involved. So parameterized in such a way that we can watch positions of the minimum, positions of the maximum, the difference in energies between the vacua, and the asymmetry of the potential, which is measured by the third derivative of the position of the maximum. Then we decided to go kind of analytic, because it turns out you can devise quasi-analytic, well, analytic formula, approximate analytic formula, which follow the strength of the signal at the location of the peak and the frequency of the peak. So you can devise explicit formulae for omega for the energy density at the peak, and for F0 for the frequency of the peak, and then using this approximate form and approximate analytic form of the potential and parameters which are in, which is one of the parameters is, well, which describes the amplitude of the energy density is called curly A, the other are sigma walls, so wall density, and so on. We were reading these parameters from the evolution of the domain wall networks, and then we were plugging into this analytic formulae. This way we were able to obtain such a plot. Well, here is the prediction of the positions of the peak of the signal of the domain walls on domain wall network from the reasonable extensions of the standard model. So essentially, the parameters are taken in such a way that the previously obtained spectra are located somewhere near this strip. Still, it looks like the strip is very far from the region where the signal could be observed. So it looks like maybe there is some physics from exotic physics coming from the early universe, but we have to devise an interesting and ingenious scenario to have the access to that physics. So that's the situation for today. Thank you very much for your attention.
Microphones work. Anyway, in fairness to the last speaker, I think we'd better move on without questions, if you don't mind. Okay, so thank you for the talk. Well, I mean, I think we need to move on to the last speaker, really. Yeah, so the last speaker. Was Salvatore.
Hello, I am here. May you hear me?
Oh, okay, sorry. Hello.
Okay, okay. So I have just to share the screen and
right.
Okay. May you see the screen?
Yes, you can see it. Do you want to make it full screen and then?
Yeah. Okay. Okay, it's okay.
Yeah, that's perfect. Thank you.
Thank you so much, and thank you to Nick, and thank you to Nick and George for inviting me in this very nice conference. And I'm sorry that I cannot stay with you in the fantastic Corfu. Okay, so let's go to my talk, and I would like to discuss with you the possibility to get the energy momentum pseudo tensor in any theory of gravity, and in particular in higher order theories of gravity. Sorry, probably there is someone that has the microphone on. Oh, okay. Okay, so why it could be interesting? It could be interesting because, according to this, it is possible to discuss in detail the gravitational radiation, as I will show you at the end of this talk, and to see that several features of theories of gravity can be, in some sense, endowed with the structure of the energy moment, the gravitational energy momentum pseudo tensor. Okay, so coming to the summary, I would like to discuss the feature related with the gravitational energy momentum tensor in terms of general relativity, and then to show you how this could be related with the extended theory of gravity. And in particular, I would like to discuss the fact that in any case, it remains a pseudo tensor, and then it is an affine tensor in some way, and furthermore, it is really strictly related with the fact that it is not possible to localize exactly the energy in general relativity. Okay, coming to the content of what I'm going to discuss with you, I would like just to give you a sort of quick overview on the energy momentum pseudo tensor in general relativity, and then enlarge the discussion to higher order theories of gravity. And I would like to show you that also in this case, this tensor is non-covariant, and then it is an affine tensor. Furthermore, I would like to discuss the possibility to get an average of the energy momentum pseudo tensor, and then to calculate the power emitted in the gravitational radiating source according to this mechanism. Okay, so the talk is based on these two papers written with my collaborators, and then let's go to the topic. There are several definitions of energy momentum pseudo tensor in general relativity. In particular, there are the definition related by with the Einstein prescription, with the Landau-Lifshitz prescription, with the Papapetrou, with Weinberg and Möller. And in any case, come out the non-tensoriality and the affine characters of this object, and which is connected, strictly connected with the fact that energy and momentum cannot be localized in general relativity. This means that essentially, this means that the possibility of not defining the energy momentum as a tensor give rise to a problem with the interpretation. In particular, it is important as a prescription to define the fact that the energy momentum of the total gravitational field is independent on the coordinate if you are considering an asymptotically flat spacetime. Then this is strictly connected with the fact that the tensor is related with some physical condition, with the asymptotic flatness. Okay, in order to define the object, it is important to define the continuity equation. In special relativity, we know that it is connected with the derivative of the energy momentum, while in general relativity, you have that in principle, this is not a conservation law, and then it should be something more difficult in order to localize this object. This is a very important argument discussed by Einstein, by Hilbert, by Noether in their first papers related with general relativity. Okay, so in order to localize the energy, Einstein postulated the possibility that exists a pseudo-tensor which is related with the energy momentum of the gravitational field, and then according to this, is it possible to construct this kind of...
Salvatore, can you just make it one slide on the screen instead of, we can see two slides.
Okay, I don't know how to do this. Sorry, I don't know how.
Oh, okay.
It's okay now? It's okay now? Is it okay now?
Oh, yeah, that's
yes.
Better.
Ah, perfect. Okay, so according to this localizability, in this case, we have to choose a space-time domain, omega, and we can consider a spatially asymptotic flatness according to this and ask for the Gauss theorem. And then you can define the energy momentum of the gravitational field plus an energy momentum related with the non-gravitational field. According to this, you can derive this quantity, which is a vector, which can be defined in a spatial hypersurface, in a volume. And then, according to this, you can construct your conservation law. Okay, so in particular, it is possible to enlarge this to any theory of gravity in which you have higher order terms. In particular, for example, this could be really interesting for fourth order theories of gravity or for higher order theories of gravity, depending on the various derivatives related with the metric of the object. Then, taking into account any Lagrangian, and in this Lagrangian, considering higher order derivatives of the metric, you can consider the variation with respect to this metric, and then you can take into account the variation of the metric tensor according to this approach. When you are doing this, thanks to the Noether theorem, you can construct the metric variation, and you can obtain a continuity equation. In the papers, there are all the details related with the calculation. And then we can obtain this gravitational energy momentum pseudo-tensor, which is this object, and This object, for example, depends on the fourth order derivatives of the metric. And then why it could be interesting? Because in this case, you are not strictly related with the fact that you are assuming a theory in which you have linearity in the Ricci scalar, but you can take into account any combination of the curvature invariant. Okay, so in going on in this kind of calculation, you can construct, in particular, this energy momentum pseudo tensor, and for Lagrangian of order n, for any order of Lagrangian. The calculation is quite cumbersome, but is nothing else but some algebra in which you have to take into account the various terms and the commutation of this kind of situation. And actually, the theorem is that if you have a Lagrangian of order n, you can get that your tensor, your pseudo tensor, is depending on two n-1 derivatives in the metric G mu. I will show you that this characteristic is very, very important for the further calculation. Also, in this case, you can take into account the continuity equation, and then the continuity equation, you can ask for conservation of your object. So consider the fact that according to this, you can take into account the gravitational part and the non-gravitational part, which contribute to the energy momentum of the system that you are taking into account. And then the conserved quantities are not only the energy and the momentum which are associated to the matter and the non-gravitational field, but the overall contribution of this field. And then, according to this, you have to be very careful in defining your conserved quantities. Okay, so exactly like in general relativity, you can consider the overall contribution in a given volume. In this case, this volume is a sigma. You can define this vector, which is this vector p, and these conditions are realized, for example, for isolated systems. And in that case, it is possible to derive the spatial asymptotic flatness. This is extremely important as soon as you are going to calculate the gravitational radiation related with this kind of object. So, because in such a case, you can define a source and the emission related with this source. Okay, so according to this, it is possible to show the non-covariance of the gravitational energy momentum tensor. What does it mean? It means that as soon as you are considering a diffeomorphism related with this object, you can find out the non-tensoriality according to the fact that is this J is the Jacobian matrix and the inverse Jacobian matrix. As soon as you are doing the transformation, you get an extra term, and this extra term is essentially related with the fact that you get these further terms. So according to this, the gravitational energy momentum tensor is not only non-covariant in general relativity, but at any order of this kind of development. And this is quite straightforward due to the fact that the non-covariance of the metric tensor derivatives is the main ingredient giving rise to this kind of property for these objects. And this can be demonstrated for any order. So why it could be interesting and why it could be related with the gravitational radiation. Imagine that you have, in this case, terms coming for example, for higher order terms, in particular Lagrangian, which can be related, for example, with the Starobinsky Lagrangian, or Lagrangian related with the higher order corrections and so on. And for any of this kind of Lagrangian, it is possible to calculate, according to the Euler-Lagrange equations, a part depending on general relativity and a part depending on these extra terms. And then it is interesting to see that in order to see if the object is physical or not, you can consider the perturbation related with this, and you can impose the harmonic gauge, which can be related with this kind of object. And immediately you realize that H mu nu terms is evolving like 1 over R, then it is a potential, a gravitational potential, and then the derivative evolves like a force, 1 over R squared, while the energy momentum pseudo tensor is evolving like 1 over R fourth. Okay, so according to this, you can construct a very general object related with any kind of correction. The corrections are the higher order terms that can come out, for example, from a loop approximation. If you consider higher order loops related with the gravitational field, for example, I have in mind the book by Birrell and Davis, in which you can take into account higher order terms, and then you can construct an energy momentum pseudo tensor for any higher order Lagrangian. And at the end of the day, this is the results. And it is interesting to see that the GR part can be, in any case, put in evidence with respect to the higher order terms, which are related with this. Okay, so all these calculations and all these mathematics, how it could be useful, and how we can use this in order to connect this with, for example, with gravitational wave physics. In particular, for example, if you can construct, in any case, the same terms that we derived before, we can construct a continuity equation also in the case of box KR gravity. And then also in this case, you can consider the energy and momentum contained in a given spatial volume. And according to this, you can construct a 4 vector, which this P mu vector is in some sense related with the propagation of the object, which is taking into account in this kind of discussion. Okay, so if you consider an harmonic gauge and you construct the weak field limit of the energy momentum pseudo tensor for Lagrangian of any order, and you expand your matrix up to the H square in harmonic gauge, and then you consider this kind of expansion, then you construct nothing else but the gravitational wave theory, you get this formula, and this formula is essentially related with the fact that you can get the energy momentum pseudo tensor in the weak field limit at any order. However, also in this case, you have to be careful in taking into account the asymptotic behavior of this object in order to get the asymptotic flatness, and then to consider physical quantities related with your tensor. Also, in this case, you have to consider, for example, the various terms, but it's very straightforward to see that these box R terms can be developed in terms of derivatives and of combination of your metric. Then it is interesting to see that according to any correction, you can construct some particular case. In particular, if you take into account P0, immediately you get the standard fourth order Lagrangian, the Starobinsky Lagrangian R plus H0 R squared. And then according to this, you get the terms related with the energy momentum pseudo tensor, in which you can easily see the box terms which give rise to the contribution which are related with the gravitational waves. It is a combination of the gravitational wave equation. On the other hand, you can continue the story, and then you can take into account P equal to 1. In this case, you have another correction which is related with these sixth order terms. And in this case, as you see, the object became more and more involved. But in this case, in any case, you can control the order according to the box, the D'Alembert operators coming into the game. Okay, so how we can use this for physics? in some sense, if you take into account the average of the energy momentum pseudo tensor, you can construct the emission related with this. And then exactly like in the case of the gravitational waves, you can construct h mu nu, you can take into account the amplitude related with this, and then you can get that this Bm is the amplitude related with your case. And according to this, you can classify the waves that you can produce according to the amplitude that you are going to generate in these terms. So essentially, what you get that you have the standard gravitational waves and the modified gravitational waves, which are related with this kind of object. And then, in some sense, according to this average procedure that you can construct, immediately you get that the average of the energy momentum of pseudo tensor give rise to an expression in which the entries are the polarization tensor that you have into the standard theory of gravitational waves. And then according to this, you have that at any order, you can consider the contribution that you have related with the polarization tensor. And then immediately you can calculate the emitted power of a given radiating source that you can take into account. And immediately you can impose the TT gauge exactly like in standard theory of gravitational waves, and then you can derive this expression, and in this expression you can see the various terms related with the average tensor component. And then essentially this part is the standard GR part, while this part is the parts related with the fact that you can take into account these higher order corrections. And then essentially the P is the index that is in some sense leading the corrections that you can take into account in the power emitted according to the gravitational radiation. If we can perform the calculation, and then we can choose the various cases, and according to this, you have that if you take into account the first term, R plus A0, R0, immediately you have that as soon as you drop this term, immediately you get the standard GR, while this is the contribution related with the fourth order gravity in particular. If you have a sixth order gravity, and then you can take into account also these terms, in this case, you can develop and you get this farther frequency. So it is interesting to see that as soon as you are assuming two orders into the development of the gravitational fields, according to this, a new frequency come out. So essentially, the theorem is that if you improve of two orders, the order of your field equation, you get a further terms. For example, sixth order gravity, you have three interesting modes. If you have a fourth order gravity, you have two interesting modes, and so on. So, for example, if you have eighth order gravity, or in this case, you get this kind of terms. It is interesting that this realize what is already sketched in a old paper by Gottleber, Schmidt, and Starobinsky, in which they demonstrate that if you improve your theories of box KR with respect to general relativity, you get K plus 1 scalar fields. In our case, you get corresponding to this, you get further modes, further gravitational modes. So this is extremely interesting. This approach is extremely interesting because according to this, you can have a very easy and very straightforward way in order to construct other terms coming from theories of gravity. And this could be useful in order to classify and then to retain possible new theories of gravity according to this kind of development. In a sense that, for example, for multi-messenger astronomy, if you are capable of selecting further modes, these further modes can be in some sense related with the gravitational radiating source and the power emitted in relation with this T3 component of the energy momentum pseudotensor. Okay, so coming to the conclusion, what you have, that using the Noether theorem for rigid translation is a very theoretical argument. Is it possible to derive the gravitational energy momentum pseudotensor in a curvature-based gravity theory at any order? This is extremely interesting if you want to develop a sort of higher order terms which are related with effective theories of gravity, for example, in curved space-time. If you want to derive an effective quantum field theory, you get these higher order terms, and then you can classify this kind of higher order terms in relation with the gravitational energy momentum pseudotensor. There is another important issue which is related with this. The important issue is that you can do the same with the non-local gravity, and then you can do the same if you take into account box -1r. Why this is interesting? Because, as you know, non-local gravity could be extremely interesting in order to investigate gravity in regimes which could be in some sense quantized. It could be the first approximation for quantum gravity. There are very nice studies in this moment in which non-local gravity is seriously considered. Also at infrared scales, for example, in relation with the dark energy and dark energy issues, for example. It is impossible, it is possible, sorry, also to derive gravitational energy momentum tensor if you take into account a metric affine theory, in particular in terms of Palatini formalism, because this could be interesting, because in such a way we are not fixing a priori the gamma, and then we are not fixing the fact that the energy momentum tensor is related with the Levi-Civita connection. So this could be interesting for this. And in particular, this could be used, for example, also if you take into account teleparallel theory of gravity, because in teleparallel theory of gravity, you can develop this kind of approach. And in such a case, the energy momentum pseudotensor could be a formidable tool in order to say what is the very important, the very fundamental nature of gravity. If gravity is metric, is non-metric, or is in particular affine theory. And then according to this, you can reconstruct your theory of gravity taking into account the properties of the pseudo energy momentum pseudotensor. So also in these cases, is it possible to calculate the power emitted by any gravitational radiating source, and in particular, these new gravitational modes can be derived with respect to GR, and then if they are detected, if any, in such a case, you can see what kind of theory is related with them. Okay, thank you. This is all what I would do.
Thank you very much. Thank you for that talk. Are there any questions in the room? Claudio's got one.
For the talk, I'm Claudio Coriano. I mean, this one of our box art theories appear in the conformal anomaly. If you take, I mean, if you just have the gravity person, just a scalar field, and you include the corrections, it's conformally coupled, then there's some kind of back reaction, and this back reaction, you normalize it with some standard counter terms, and then you get exactly the expansion. This is one of our box art terms. Now, the thing I'd like to ask you is, would it be possible, let's say, to include this type of analysis, eventually quantum correction to the stress energy tensor?
Yes, yes. Thank you very much for this question.
So I say it now. What happens, for instance, if you take level of gravity, which is second order in various dimensions and so on. I mean, in that case, you should have a significant simplification, I guess.
Yes. Thank you very much, Nick. This is a very important issue. In some sense, we can use this approach in order to have a sort of inverse scattering, in a sense that this kind of quantum corrections could be, in some sense, included into this pseudo-tensor. And then, according to the properties of this pseudo-tensor, you can reconstruct the theory of gravity, which is interesting. Why it could be interesting? Because imagine that, do you know that according to the multi-messenger approach, you can derive, it is some theories of gravity are not excluded. There are several papers in which they say that there are windows in which some theories of gravity are not excluded. In particular, Lovelock gravity, which is a very wide family of gravities, is not excluded a priori. And it is interesting to see that most of these kind of theories are inside the Lovelock classification. So I try to answer to your question. Is it possible, in some sense, according to the, imagine that you detect a farther mode in the gravitational waves. These farther modes, if can be included in this kind of formalism, can help you in order to reconstruct the theory of gravity by which it comes. So, in my opinion, yes, my answer is yes. The Lovelock approach can be exactly developed, the Lovelock theories can be developed under this standard, and according to this, you can also include the quantum corrections. I hope that I have answered your question.
Yes, yes. Okay, thank you very much. Thanks.
Welcome.
Okay, any more questions? All right, then I think we'll bring the proceedings to a close. Thank you very much.
Sorry, Stephen, can I ask, it's Nick Mavromatos from the Zoom. Can I ask a very quick question?
So, we have one from Zoom, yes, and Nick Mavromatos.
Sorry. Hi, Salvatore. Nice talk.
Hi, Nick.
How are you? The question is, when you extend it to torsion, if you have in supergravity theory where the torsion consists of fermions, does your construction go through there as well? Or?
Yes, it worked. In this paper we discusses this.
Very good.
In this paper, with torsion, probably torsion is better because I can answer you. This is better because, for example, in torsion, when you use, for example, the Weissenbach connection, it is affine by construction. So for supergravity, I think that it is better. It is very good, this kind of formalism.
Very good. Thank you very much. Thank you.
You're welcome.
Okay. Any more questions on Zoom? No. Okay. Right then. So thank you very much, Salvatore.
Thank you.
And thank you all the speakers.
Okay. Thank you. Bye. Ciao, Nick.
Ciao, Salvatore.
Ciao, George.